Well, hi, everybody. One of the primary objects in abstract algebra is the concept of a group. A group is just a type of mathematical structure that has a variety of rules associated with it, and from which we can derive a lot of examples. In this video, I'd like to just give you a basic introduction to groups, the basic definitions and examples behind group theory. And of course, the definition of a group is where we're going to start. It is motivated by the fact that it shows up in the real world, this particular structure with these particular rules. They show up in the real world in a variety of places. And so as soon as I get the definition on the board, we'll turn to some examples of groups. So let me go on up and start talking about the definition of a group. I'll put that right here for you. A group, which is usually written with a G, a capital G, and there's always some kind of an algebraic operation associated with it. So for the purposes of the definition, I'll call that star. So a group, I'll underline whatever word I'm defining in my definitions, is a non-empty set. It's a non-empty set, which is what we're calling capital G. It's a non-empty set together with this operation that I talked about, which is star. And star, if you want to think of it, it's actually a mapping. It's actually a function that takes two elements that are both in the group G, right? So I'm writing this as G cross G. It's almost like G squared. It's just two elements of the group, and it spits out another element of the group as an output. So we can view this as a function. So in other words, what's going on is we're taking in, let's say, two elements, little a, little b from the group. And this star function is going to spit out the resulting element, which I'll just denote as a star b. Okay, so this is just kind of the way a function could be written explicitly. And this has to satisfy, so this is satisfying some rules. So I just want to talk about what are the axioms of a group? What are the requirements, the definitions of a group? So there's a few of them, and you're going to want to learn these. The first one is what's called closure. And you would see this with any abstract algebraic structure, whether it's a vector space or a group or a ring or a field, whatever. There's always a closure requirement, which just says that for all A and B that belong to the group G in the first place. Okay, so closure just means that if you start with two elements that are in the group to begin with, then we have that the result, A star B, the result of sort of multiplying together the elements of the group, results in another element from the group G back again. Okay, so if we start with two elements in the group, the result has to remain inside the group. That's a standard requirement. The second axiom is called the associative property. So I'll just write associative here. And what this means is that if we take three elements, so let's say for all A, B, and C in the group G. So if I take three elements, A, B, and C from the group G, then if we were to multiply B and C together first, and then pre-multiply that by A. So that's what this is here, A star, the quantity B star C. We should get the same result as if we first multiply A and B together and then apply C. Okay, in other words, what this is really saying, guys, the associative law is really just saying parentheses don't matter. When you're writing out sort of a list of elements of G that have been multiplied together under the operation star, it does not matter how you parenthesize that expression. Okay, so we can actually leave them out, right? So you'll see a lot of times that, I'll just simply write this as ABC. because there can be no confusion about whether the A and B comes first and then C, or whether we do B star C first and then pre-multiply by A. It makes no difference. We're going to get the same result either way because it's required in a group. That's one of the axioms. Okay, great. The third axiom of a group is the identity element. So I'll call that identity here. Okay, and this just says there exists some element. It's often called little e. So E is an element of the group. There exists this element E such that A star E is the same as A, which is the same as E star A. Okay, those are all the same, and this is for all A in the group G. So in other words, it's like multiplying by 1. Right? Under multiplication, you can kind of think of the number 1 as if it was an identity element. Because when you multiply 1 times anything, you just get that same thing back again, right? That's what this equation here is saying. If we take A star E or E star A, makes no difference. We're just going to get A back again. All right, and then one last axiom here. The fourth property is the requirement of inverses. So we are required to have inverses. And so what this says is that for all A in the group G, okay, there exists another element. I'm going to call it D. So D is another element in G such that A star D is equal to the identity element E, which is the same as D star A. Okay. Notice that the identity element is mentioned in the inverses axiom. So before you can talk about inverses, you kind of have to establish the identity element first. You have to know what is E. Make sure it exists and what is it, right? Once we know that there's an identity element, then we can ask whether the elements in this group have inverses. So that would be required for it to be a group, actually. So every element has to have an inverse in a group. These are the 4 main axioms of a group. Now, I should point out that many mathematicians have interest in things that are close to being groups, but not quite. So for example, if we only require a group, if we only require a structure to be closed and associative, that's already a structure. That's already an algebraic structure that may draw interest for certain types of mathematicians. If we just require closure and associativity, just for your information, we won't be studying this a lot in this abstract algebra course, but they are called semigroups. So a semigroup is just an algebraic structure that has closure and the associative property. And we're not requiring it to have an identity or inverses. If the structure actually has closure, associative, and an identity requirement, then those structures are called monoids. Okay, so a semigroup has to have the first 2 requirements. A monoid has to have the first 3. And of course, a group has to have all 4. So notice that a group would always be a monoid, because if you're a group, you have all of the axioms that I've listed here. So of course, it's automatically a monoid. And if something is a monoid, well, then it would automatically be a semigroup. Because if it's got the first 3 axioms, if you have a structure that satisfies the first 3 axioms in this list, then of course it satisfies the first 2 axioms in the list, which means that a monoid would already be a semigroup. Okay, so these are the requirements that have been spelled out for what is a group. What I'd like to do next, guys, is add a couple of additional definitions or maybe notations that are sometimes associated with groups as well. So just, I'll call this another definition down here. Okay, and what it says is that if, in addition, so if we have another additional axiom, namely that A star B, notice it's not required in my list of 4 axioms, but it might be the case that A star B is equal to B star A. And if that's true for all elements in the group G, right, then we say that G is abelian. It is then called an abelian group. That's an additional sort of optional axiom. So there are groups that are abelian, and there's also groups that are not abelian. And of course, if a group is abelian, you have this extra axiom here. That actually really makes a difference in terms of understanding what those kinds of groups would look like. So abelian groups, if we think of that as like a family of all abelian groups, they are fairly well understood by mathematicians. By the time you throw in that 5th axiom as an additional requirement, you now have enough information, and mathematicians through the years have had enough leverage to be able to describe what do all abelian groups look like. And we're actually going to talk about that in this course. So abelian groups are very, very well understood. Okay, let me take just a little bit of space here at the top to write down one more piece of notation, and then we're going to spend the rest of this video primarily just doing some examples. So I'll just point out that if G is finite, in other words, if there's a finite, it doesn't have to be finite, but if it is finite, right, we denote its size. Its size. How many elements does it have? That's the size. It's also sometimes called the order of the group. I like to use the word size though, because order gets used for other things and just to keep it separate. But the size of a group is just denoted this way. We kind of put these little absolute value bars on it to sort of tell what its size is. Okay, great. Well, I'm going to now take a few minutes and give you some examples of groups. Some of them will be abelian, some will not. Some of them will be finite, some will not. We're going to take a look at some examples. I am going to erase this definition. So these 4 axioms here are very important to the definition of a group. If you need to pause and digest this a little bit more or get any more of it written down, this would be a great time to do that. I am going to erase this, and I'll be referring to these axioms as we talk further into this. Okay, so let me do that. We need quite a bit of room. We're going to show a lot of examples of groups, and some of them are going to be very familiar things, and others maybe not quite so familiar. So there'll be some new structures here, and then there'll be some familiar ones. I think I'm going to start with, what would be probably some very familiar examples of groups that make sense that I would start with that. So let's get some examples of groups going. So the first example of a group here, well, we could take, for example, the integers with the operation of addition. Okay, so let's just think about this for a minute. You have those 4 rules that you have to check. I'm not going to write them all down because they're pretty obvious, actually. You've probably been working with integers your whole life. You know, for example, that it has closure. If I add 2 integers together, I get another integer. Okay, it's associative. A plus B plus C always gives you the same answer, no matter sort of how you take those 3 elements and start adding them together. Okay, so the parentheses won't matter when I add integers together. There's an identity element. I bet you know what it is. By the way, you can always stop and pause if you want to think for yourself before you hear me just blurt out the answer. Feel free to pause these videos at any point so that you can do your own thinking. It always helps to do that, I think. But in the case of the integers under addition, which element is like the identity element? Well, the answer under addition would be 0, because 0 plus x is always equal to x, right? So we don't have to worry about that. Additive inverses or inverses, what element, if I take A and I want to star it with D, will get me back to 0 again? Well, the answer is that you would just take the negative of whatever A is. So the inverse of 3 is -3. The inverse of 8 is -8, and so on. Every element has an inverse. And actually, the integers are in a abelian group because A plus B is the same as B plus A, right? So we know these things. This is not an unfamiliar type of a group that we're talking about here. And while we're at it, I'm just going to continue this as the first example. If I can get away with all of that with the integers, then I could, of course, enlarge my set to be the rational numbers. So this would just be, the Q is the rational numbers. So this would be all fractions, right? Again, using the operation of addition. We could go even further and extend that to the real numbers. The real numbers under addition have all of those same properties. The axioms are pretty much clear in the same way that they are for the integers. So we have the real numbers, and then of course we also have the complex numbers under addition. We have all of these. All of these are great. So these are all, they are infinite, by the way, none of these are finite, but they are infinite abelian groups. Okay, now we do have to be a little bit careful. Because if we try to get, so here we were going for larger and larger sets, right? The real numbers, the complex numbers, those are really big. They include the integers. If we try to go smaller, for example, let's suppose that we took just the natural numbers under addition. The natural numbers, just to remind you, those are literally just the positive integers. If you do that, you now have a problem, right? Because that identity element that we have as being 0 in all of these examples here on the first line, we no longer have 0 in the natural numbers. So we have lost the identity element. And so the natural numbers is not a group. It does not form a group. It will, however, form a semi-group. Okay, if you add 2 positive integers together, you'll still get another positive integer. And the associative property of addition is still going to be true for those positive integers as well. So it does satisfy the requirements of a semi-group, but it's not a group. It's not even a monoid, actually. The monoid, remember, had to have the identity element, and we're missing that here. Okay, so that's the difference. Okay. So those are all great first examples of groups. They should be pretty familiar. They are abelian, which is nice. One thing that's tempting to think about with these examples is whether we could change the operation from addition to multiplication. Remember, I was using star for the notation about the operation in the group. So the star, is just a symbol that could represent any mathematical operation that we want to define. And so here we've been looking at addition as being the primary algebraic operation for the groups that we've looked at in the first example. But it always comes out to be a question, well, what about, can I just change the addition to a multiplication, for example? Well, let's just take an example. If I took the real numbers under multiplication, so now I'm just going to multiply real numbers together. The question I would like you to think about, and you can pause the video if it would be helpful to think about it for a moment, is whether or not that will be a group. So, it's got the 4 requirements, right? The 4 rules that we wrote down in the definition. Closure. So if I multiply 2 real numbers together, will I get another real number? The answer is yes. Okay. We don't have to write a whole lot out about that. We're just thinking about this out loud. Okay. The associative property, if I multiply numbers together, doesn't matter how I parenthesize them in terms of doing the binary operation. It really doesn't, right? The multiplication works no matter how I set that up. What about an identity element? Under addition, the identity element was 0 up here in the first example. But under multiplication, of course, I'm going to need to change that identity element to the number 1. So 1 times x will be equal to x, right? And so that's fine. So we have an identity element, which is 1. But now this leads us to a little bit of an issue, which is if the identity element is 1 under multiplication here, does every element have an inverse? Well, you might think, well, the number 3 has an inverse, which would be 1/3. 3 times 1/3 is 1. 7 has a multiplicative inverse, which would be 1/7, because 7 times 1/7 is 1. Does every real number have a multiplicative inverse? If you think about it for a minute, there is a problem, and that's the number 0. 0 is a real number, but I cannot multiply it by something and get 1. Because when I multiply 0 by anything, I'm always going to get 0. So this is actually, it's close, but it's not a group. This is not a group. And what we can say here is that 0 has no inverse. That's actually really the only problem with it. So here's what we're going to do. And this is what you're going to see me do with some other examples as well. If there's sort of a bad guy in my set that fails this axiom of a group, I'm just going to get rid of it. Okay. So what I'm going to do is I'm going to get rid of 0. And I'm going to create a new structure, which I'm going to write as R star. Okay. And we're going to consider this under multiplication. Actually, so before I actually define the group, let me just define R star. I am going to get rid of 0 from the real numbers. I'm just going to take it out of the real number set. And so I'm looking at the non-zero real numbers. And if I do that, now I have R star under multiplication, which is a group. So there's a group under multiplication obtained by just getting rid of 0. And similarly, right, because all of the other axioms are okay. Closure is okay, associativity is okay, and my identity element is the number 1. So similarly, if I look at the non-zero complex numbers, or the non-zero rational numbers, we can look at any of these. We could even look at the well, let's be careful. These are groups. Let's start with that. However, I should point out that even if you throw away 0, even if you throw away 0 from the integers, you still don't have a group. And why not? Well, what's the inverse of 3? Under multiplication, the inverse of 3 should be 1/3. Problem is 1/3 is not an integer. It's not in the set. So this is not a group. Even after we try to make that remedy where we get rid of 0, we still don't have a group when we look at the non-zero integers. We would have to get rid of all of the integers that don't have inverses. Actually, that would be which elements? We'd be getting rid of 2, 3, 4, 5, and so on. The only thing that we wouldn't get rid of would be the 1 and the -1. So at that point, you have a very, very small group, which is just plus and minus 1 under multiplication. That's okay. That is a group. It's just not that interesting of a group. Okay, hopefully so far so good. Let's take a look at a different example of a group. By the way, all of these are groups, and I should mention in this second example that these are actually abelian groups. Right, the multiplication is commutative, A times B equals B times A, and so on and so forth. Let's take a look at another example of a group. Let's take our set to consist of matrices. Okay, so I'm going to actually make these n by n matrices. I'll write it in this notation if that's all right. MAT sub n of C. These are n by n matrices whose entries are complex numbers. I'm going to do this under addition. Okay, and this is an abelian group also. Your identity element is just the big zero matrix, right? The matrix where all of the entries are just zero. Certainly, if you add two of these together, you add two n by n matrices, you get another n by n matrix. Parentheses don't matter under addition, no problem there either. And the inverse under addition, keep in mind, I'm using the operation is really critical, isn't it? We have to keep in mind, what operation are we using? Under addition, the inverse of a matrix is literally just the negative of that matrix, where you just put minus signs in front of every single entry within the matrix. So all of those axioms are true, and matrix addition is actually commutative as well. A plus B is the same as B plus A. So this forms an abelian group. So you know where I'm going to go with this next, right? I'm going to ask, well, what about under multiplication? The same thing I did with the first two examples. I said, okay, all of these groups under addition, we want to try to turn them into groups under multiplication, but we had to get rid of some element that did not have an inverse under multiplication. So we got rid of the zero, right? What about with matrices, n by n matrices? Well, as you probably remember from your linear algebra course, if you look at the n by n matrices, right, we have to be careful because they don't all have inverses. You spend a lot of time talking about inverses of matrices under multiplication. And not all matrices have inverses. You hopefully remember that an n by n matrix will have an inverse only when it has, for example, a non-zero determinant. Remember that? The determinant has to be non-zero. So we should point out, again, I'll just add it here, that not all matrices, of course, have a non-zero determinant. So there's going to be matrices. Let's do it here. If we try to look at the n by n matrices under multiplication, this is not a group. It's not a group at all. Okay. So let me go up to the top and let's try the same trick that we did with the real numbers. Let's do that here. Let's just, we're kind of going to cheat, guys. We're just going to throw out any matrix that doesn't have an inverse, and whatever we're left with is going to be those matrices that have multiplicative inverses, and we can make a group out of them. It's exactly what we're going to do. So for our fourth example, right, I'm going to, so in this case, we're not just going to put a star on the notation. There's actually a whole nother set of symbols for this. We're going to write this as GL n of C. The GL stands for general linear. So this is going to be called the general linear group. And what is it? What is GL n of C? This is simply the set of matrices. I'll use capital A for a matrix. The n by n matrices such that A is invertible in the classic linear algebra sense. Okay. In other words, I'll just write it down here one more time. It's those n by n matrices such that the determinant of A is not 0. Okay, so a little bit of linear algebra thrown in here on this example. So if we keep only those matrices that are invertible under multiplication, then we're going to be good with having a group. If you multiply two invertible matrices together, you get another invertible matrix. Does matrix multiplication have to be parenthesized? No, we learned this in linear algebra. A times B times C, right? With 3 matrices, it doesn't matter how we add parentheses to those expressions. It is associative, okay? And of course, we have an identity element. The identity, just to remind you here, the identity element is often written as I sub n, and this is literally just the n by n matrix. So just remind you about this. It's a matrix that has 1s on the main diagonal, and it has 0s everywhere else. So if you multiply by that matrix, nothing happens to the result, right? So it's like multiplying by 1. And now, although not every matrix has an inverse under multiplication, we have created a set in a somewhat artificial way by just throwing away those matrices that don't have inverses to begin with. And what we're left with is this set, which does satisfy the inverses property. So if we do this, then create this, then GL n of C under multiplication is a group. And I'd like to remind you that matrix multiplication is not commutative. So this is a non-abelian group. So here we have an example of a group that it is a group, but it's not abelian. It's a non-abelian group. Okay, so there you go. There is a good example of a group that comes out of linear algebra. I should make a note as well before I go any further that you notice I put the complex numbers in here on these last couple of examples. We could just as well use any other scalar set that in and of itself forms a group. So for example, we can talk about mat sub n of R, mat sub n of Q, and mat sub n of Z. These are all abelian groups under addition. And GL n of R, GL n of Q, and GLN, I'm not going to use the integers here because again, under multiplication, most things don't have inverses. But these are non-abelian groups, just these two are non-abelian groups under multiplication. Okay, so you can restrict your scalars to be just rationals or reals. You don't have to use the complex numbers for these. I should actually also mention that if we go back to the addition again, the matrices don't even have to be square size, right? They don't actually have to be n by n. When you're doing addition and it's all just slot by slot computations, it's perfectly okay to use m by n matrices. They don't have to be square, but I won't write that one down. Normally, of course, the typical examples will be with square matrices, okay? But hopefully you're getting the theme here that if I want to turn an additive group into a group under multiplication, notice how in these examples that we've shown so far, I can do that if I simply remove those elements, those objects that don't have inverses under multiplication. Okay. Whew, take a breath. Hopefully everything's so far so good. I'm going to show you a few more examples of groups here. Let's just go ahead and continue. So for my next example, number 5, this is one that should be familiar from maybe a previous abstract algebra course. We can look at the integers in mod n. And again, I'm going to start by looking at addition in mod n. So this is a finite abelian group. We're just doing addition in mod n. And of course, the size of this group is just n, right? So if you just want to remember here for a moment with me, this is literally just the set. Do you remember this from earlier abstract algebra courses? These are just the congruence classes of the numbers from 0 up through n minus 1. And you're just doing addition in mod n, which is what this z sub or this plus sub n means. So we're doing addition in mod n, and this forms a group. Okay. Once again, you might be ready to ask me, what about making that into a group under multiplication? So let me tell you that, yes, we can do that as well. So what we can do is throw away those elements that don't have inverses under multiplication. So let me make that as maybe a 6th example. Okay, so we can form, I'll write it out in words first. We can form a multiplicative group and the notation for this one is going to be u sub n, and then we're going to have a dot with a sub n on it. Okay, so we can form this group by removing numbers. We're going to be removing numbers from Zn that don't have inverses. Now, it turns out that which numbers are those that don't have inverses? It turns out that what we're actually going to be removing, if we remove those numbers from Zn that don't have multiplicative inverses, it's just those numbers that share common factor or factors with the number n itself. So I think what'll make the most sense is if I actually show you an example of this. We come back up to the top. Okay, so by the way, this is sometimes called the unitary group. That's where the U is coming from. So as a quick example within this example, suppose that n is 12. Okay, so you're talking about, you start off, of course, C12 would just be the congruence classes of 0, 1, 2, 3, and so on, all the way up through 11. Under addition, that is a group of size 12. Okay, but then if I want to calculate what U12 is, this is going to be a group under multiplication, and it's obtained by removing whichever of these numbers shares common factors with 12. Of course, 12 is right here. 12 is just 2 squared times 3. So any numbers that have factors of 2 or 3 in them. Of course, we definitely have to remove 0, which has factors of anything. And if we get rid of 0 for sure, but we keep 1. 1 is going to be our identity element. But 2 has a common factor with 12, so we remove it. 3 has a common factor with 12. We remove it. 4 has common factors with 12. We remove it. In other words, the next number that we're going to keep is actually 5. 5 has no common factors with 12. Hopefully it makes sense so far. 6 has common factors with 12, but 7 does not. Okay. 8 has common factors, 9, 10, right? It's just a very simple little number theory idea. Last number that we need to keep is 11. By the way, notice that these two guys. Oh, I'm sorry. No. I wanted to point out that in this group, everybody is their own inverse under multiplication. 5 times 5 is 1. If I work in mod 12, right? So 5 times 5 is 25, but in the world of mod 12, 25 is the same as 1. 7 is its own inverse because 7 times 7 is 49, but in mod 12, that's the same as 1. And 11, you probably learned this trick in an earlier algebra class. 11, we can think of it as -1. That really is what it is. And -1 is its own inverse. -1 times -1 gets me back to 1 again. Okay, so my identity element is here. And I have 3 other elements, each of which is its own inverse. Okay, so that forms a group under multiplication. So this is, in fact, it's an abelian group under multiplication in mod 12. Exactly. So we have another good example of a group there. Okay, let's take a look at yet another example of a group. Feel free to stop and pause. If you need to think about any of this stuff. Make some notes to yourself. If you have any questions, jot them down and send them to me. Be glad to try to help you answer those. Oh, by the way, for those of you who've taken number theory already, and I know some of you that probably have, you might actually know what the size of UN is going to be in general. So this is just a side remark for those of you who've seen a little bit of number theory. How many numbers are going to survive after we remove the ones that have common factors with n? Well, what it means is we're keeping the numbers that have no common factors with n, right? Those are the ones that we keep. 1, 5, 7, and 11, they have no common factors with 12. So we're keeping those numbers that are what are called relatively prime to n. And there is a name for this. Again, the people who've seen some number theory will appreciate it. It's called the Euler phi function of n. It's just how many numbers are relatively prime. Okay, so this is the number of integers between 1 and n that are relatively prime to n. That's it. That's exactly what it is. Okay, let's write down another example of a group. Do another example. I think I'm on to, what number am I up to? It's number 7, maybe? Hoping I have that right. So let's talk about something called the quaternion group. And this one is denoted with Q8. So now we're getting away from things that are so familiar, right? We've been working with integers and real numbers and complex numbers and matrices and integers and mod n. These are all fairly familiar types of objects to work with. What I want to do here is finally get to an example of a group that's maybe not quite so familiar. Q8, as the name suggests, it has exactly 8 elements, and they are generally just denoted in this manner. Plus and minus 1, plus and minus I, plus and minus J, and plus and minus K. Right? And of course, your identity element is going to be the number 1. This is going to be kind of thought of as a group under multiplication, but of course, we have to just explain what multiplication means, right? Sometimes to do that, sometimes when we want to explain how to actually quote unquote multiply elements or star together elements from our group, if we're in kind of a more abstract example, like the one I'm about to describe here, it actually can be done by actually writing out what is called a multiplication table. And give yourself some room if you want to try and write this down. This is a fairly big table because we have 8 elements. And what we do is we list all of the elements across on the top of the chart. And we also make another listing of them down the first column here on the left side. Let's see if I have enough room. I think that'll work. Okay, so we just start off with this sort of blank chart. And then we just have to explain, you know, if I take A star B, then in the box that goes with that particular row and column, we're going to write down what the result is. So what I'm going to do here, of course, the 1 is the identity element. So when I star 1 with anybody, I just get that same thing back again, right? So it's going to have to be like this. And same thing down the first column. So the first row and column are kind of obvious because you're multiplying by 1, and that is being handled in the traditional manner, which is that it doesn't change the result. So what I've got on there so far is just the fact that the 1 is the identity element. Now, I have to tell you how to fill out the rest of this thing. Turns out that the -1 behaves exactly like you would expect. It just behaves like a minus sign. So if I go across, for example, -1 times -I, I get positive I. -1 times j, I get negative j. -1 times negative j, I get j. -1 times k, I get minus k. And -1 times minus k is k. Okay. And it's going to be, by the way, this is going to be the same thing in the first column here. So we'll have -I, and then we'll have I. J times -1 is minus j, and then j, and then minus k, and then k. So those are the first 2 rows and columns that we end up with. Okay, great. Now, how does the rest of this work? Well, I'm just going to tell you that basically over here, I can write down some notes for ourselves. If we take I squared, j squared, or k squared, we're going to get -1. So there's going to be a -1 there, I times I, right? I times I is -1. J times j is -1. And k times k is -1. And you can see that, well, if you had -I squared, or -j squared, or -k squared, the same thing would happen because the minus sign, when you square it, just goes away. So in fact, what we're saying here, guys, is that there's a bunch of -1s that just kind of go all the way down the diagonal of this table. Okay, so that's what we're going to have so far. Okay, but what is interesting about this is that how do we define, for example, I times -I? Well, that would just be the negative of I squared, so that's just going to be a 1. And by the way, -I times I will also just be a 1. J times negative j is a 1, and negative j times j is a 1. So we're actually filling in the corners here pretty easily, just like so. But where it gets interesting is when you take I times j, okay? I times j is going to be equal to k, which means that I times negative j is negative k. And I times k is going to be negative j, and I times negative k is going to be j. There you go. Okay, so that's the third row. And of course, we can continue this way and try to fill out the entire chart that we have here in front of us. Yeah, it's a little bit messy. I'm not going to lie to you. It's a little messy to write this whole thing out. So the -I, let me just try and somewhat quickly finish filling this out. Don't worry too much about this because you can look up this table pretty easily. The key thing here, guys, is that I times j is k, which is the same as negative of j times I. By the way, this is a non-abelian group. Notice I times j is k. But j times I, which is right here, is actually negative k. So we get a little bit of a non-commutative flavor to this thing. Okay, so we can keep going like that. J times j was -1, and then we have a 1 here. And then over here, j times k is going to be I, j times negative k is negative I. Okay, great. And then we have to fill out the next row, which is actually just the minus of the row above it. I'm going to do this somewhat quickly, guys. Just feel free to take your time. Whoops, I have not done that correctly, however. Yeah, I see. I only have like seven rows here. Yeah, it's a little bit difficult. I'm so sorry. This is not critical, guys, to dwell on this. I don't want to take up too much time. I've got half the table right here, and this half of the table looks great to me. I ran out of room a little bit to do the next 4 rows, but you know, it's a fairly straightforward thing. Let me just see this. This one should be. Well, anyway, so we could continue to fill this out. Maybe I'll try. Okay, I'll try and do this fairly quickly. If you want to sit past this because you're a little bored with it, it's okay. I'm not going to explain every single square though at this point, because it's just not worth it. I and minus I, and then this next row is just the negative of the row above it. And then the k, negative k, j, negative j, negative I, -1 and 1, and then the last row is just the negative of the second to last row. So you can take this as an exercise to fill the whole thing out if you wanted to, but that's basically how the table looks. Okay, so I think I do have it right now. It just took me a little bit of doing. This is a non-abelian group, and in this case, we've basically written down how the multiplication operation is going to work. We've kind of made it up. So this is a non-abelian group. And of course, the size of that group is just 8, right? So there you go. There's a nice example of a group that's not quite so familiar. Of course, it would have to be checked that you have closure. Closure just means that if you look at all of the entries in this chart, they all have to be among these 8 elements, right? So you can't write something down in the chart here that isn't in the original list somewhere. That's pretty obvious. What's maybe not quite so obvious is that this is associative. I'll let you think about that. It's not worth writing out every possible product of 3 things. It just takes too much time, but this will be associative. The 1 does serve as an identity element. And what about inverses? Well, 1 is its own inverse, -1 is its own inverse. So you can kind of look at where the 1s are in the table, and that helps you figure out what things are inverses of each other. So for example, I have to multiply I by -I. I times -I is 1. That means that those are inverses of each other. I and -I are inverses. J and -j are also inverses. And K and -K, those are also inverses. So that's verifying the group axioms from there, and you can kind of get the idea how that works. Feel free to pause if you need to think about this quaternion group. This is a nice example of a group. I will be using this to illustrate other concepts from group theory. So I do want you to be comfortable with sort of how this group is constructed and how it works. Okay, let me give you another example of a group. There are so many, right? Right? I could spend hours just giving examples of groups. I'm just trying to show you, you know, obviously natural ones we started with make sense to show you because you've actually seen them before. But now I'm trying to give you a few examples of groups that maybe you haven't seen before and talk about them a little bit. So the next one that I would probably take a look at is something called the symmetric group. And this is denoted with SN. And what this is let me give you the definition. This is equal to, of course, it's a set of elements again. It's a set of objects. It's the set of all bijections. I'll call them sigma. So we'll use these Greek letters to denote the elements of the symmetric group. These are bijections from the set 1 to ... up to n to itself. So you're actually talking about functions. Remember that a bijection is just a one-to-one onto map. It's a one-to-one and onto function. It's like a permutation. It's a bijection from the set to itself. And of course, I have to have an operation to have a group. A group is not just a collection of objects. It's not just a collection of the bijections here. There has to be a way of multiplying these bijections together. And the way that we're going to do that, I'll explain it right here, is composition of bijections. One of the first exercises that you maybe saw when you were studying functions and sets, maybe in a strategies of proof class, is one of the great exercises is that when you compose two bijections together, you get another bijection. So that's exactly what happens with this particular structure, because you want it to be closed. It has to have closure. If I have two bijections and I star them together, if I compose them together under composition, I have to get another bijection. Right. So that's exactly the group that we're talking about here. So just to maybe show you an example, let me work with n equals 5 for a moment. And let's talk about the symmetric group on the set of 5 numbers. So these are going to be permutations, or in other words, bijections, with inputs and outputs that are just the integers from 1 to 5. So as an example of an element that we might have, let me use sigma to describe this. A very common way of writing these elements, maybe some of you have seen this before, is that we just write the domain of the bijection on the top row of this sort of 2-line notation that I'm going to fill out. So the domain is 1, 2, 3, 4, and 5. That's just the inputs into sigma. Now the outputs have to be the same numbers 1 through 5 in some order, in some permuted order. So they could be the same order, or they could be switched. So it could be 1 to 4, 2, 3, 5, 1, something like that. And what this means is that sigma maps 1 to 4, 2 to 2, 3 to 3, 4 to 5, and 5 to 1. That's a permutation. It is, in other words, it is a bijection from 1 through 5 to itself. Okay. Let's take it. So this is an element of S5. Okay. Let's write down another element just to have some another example. Let's call this one tau. So I have sigma and I have tau. This is just going to be another bijection between the numbers 1 through 5 in itself. So let's say we have 1 to 3, 2 to 1, 3 to 5, 4 to 4, or 5 to 2, something like that. Okay. So what we can do, for example, guys, is we can compose these elements together. And I wanted to just make sure we're all on the same page with how to do that. Let's suppose that I wanted to do the composition of sigma with tau. Now, you guys probably remember that when you compose functions, you kind of work from the inside out. So like if I wanted to do like f of g of x, right? I actually start with g first, right? G is on the inside here. And then I take f of that. In other words, I'm working inside out. That's exactly what I'm going to do here too. The function that's actually on the right is the one that we start with and apply it first. So if I have tau composed with sigma, I'm going to start with sigma. So look at sigma. Sigma, where does it send 1? Let's just figure out where 1 goes. Sigma sends 1 to 4. But then on the outside of that, because we're going to go from right to left, we have tau, and tau sends 4 to 4. So we started at 1 and we applied sigma to it, and then tau to the result of that, and we end up with 4. Okay. What about 2? So if we start with 2 and we apply sigma, it goes to 2, but then 2 goes to 1. So the result is that 2 ends up going to 1. The next one, if I start with 3, sigma of 3 is 3, and then tau of that is 5. So at the end of the day, we ended up at 5. Let's take a look at the next one. Starting with 4, sigma sends 4 to 5, and tau then sends 5 to 2. So we started at 4, we got mapped to 5, and then 5 to 2, so we put a 2 here. Okay. Finally, if we start with 5, sigma will map it to 1, and then 1 will map that to 3. Or tau will map that to 3. So 5 goes to 1 under sigma, and then under tau, the 1 goes on to 3. So at the end of the day, we started at 5 and we ended at 3. Notice that what we have here, guys, is another element of S5. You're just composing bijections together. One of the beautiful things about function composition is that it's always associative. It's always associative, and so you don't even have to check that axiom of a group. Because you've composed bijections with bijections, you get bijections, closure is not an issue. What about the identity element? Let's see, the identity element is the one that should sort of do nothing. It should be the bijection, or in other words, the permutation that does nothing to an element. We're going to call it E, and you can imagine what that's going to be. It's just going to be that particular function that literally leaves everything alone. It sends 1 to 1, 2 to 2, 3 to 3, 4 to 4, and 5 to 5. That's your identity element. And if you compose this with anything else, you're just going to get that back again. What about inverses? Using the example we have on the board already, let's look at the inverse. Oh, I'm using this notation. I'll explain this notation in a minute. This is the inverse of sigma. But the question is, what would be the inverse here? The inverse is that function that sort of undoes the original sigma. Because remember, if you've done it correctly, the inverse, when you compose it with the original sigma, everything should be sent back to the identity. In other words, 1 should go to 1, 2 should go to 2. So for example, if sigma sends 1 to 4, then sigma inverse has to follow that up by sending 4 right back to 1 again. Right? And if sigma sends 2 to 2, then the inverse should also fix that same 2. 3 to 3, so the inverse will send 3 to 3. Now sigma sent 4 to 5, so sigma inverse should send 5 back to 4. And finally, sigma sent 5 to 1, so the inverse should send 1 back to 5 again. Yeah, if you have something that's a bijection, you can always reverse the arrows, right? You can turn it around. If you think about it, that's exactly what we've done here, right? 1 maps to 4 under sigma. So under sigma inverse, you see, we've just turned it around. 4 goes back to 1, but that's just like flipping the top row with the bottom row here. If you read this from the bottom to the top, It looks just like sigma in the reverse direction. It's kind of cool. So I hope that that makes sense. I will point out that when you do composition of functions, order matters, right? In other words, so if I come over here and I do G composed with F of X, you're not going to necessarily get the same result. If you do two functions in the opposite order, so for example, if I did the sine of x squared, so for this function, I have squared a number first and then taken the sine of it. That is not the same thing as first taking the sine of x and then squaring the result. Those are not the same, just from calc as a nice little calculus example. So this is not abelian, right? So I'll just make a note here, Sn, this is an extremely important group. Please learn it well, right? The symmetric groups are really important, but this is a non-abelian group. And while we're at it, maybe you want to pause me for a moment and think about it. What is the size of this group? That would be a good question. Good question to think about. How big is this group? We're talking about permutations, right? We're talking about permutations here. It's almost like, okay, so we're going to, let's come back here. If we wanted to create an element sigma, so like how many ways could I fill out the second row so that it's a permutation? In other words, every number from 1 through 5 has to be used exactly one time. It's a little counting problem, isn't it? Right. So if I start from the left here and I want to say to myself, how many places could I possibly map the 1 to? The answer is I can map it to 1, 2, 3, 4, or 5. There are 5, or in other words, n choices. So I have like n choices right here. Let's just say I pick something. Let's say I pick 4. Okay, great. After I've done that, now the question is how many choices are left for what number I put in the second image position. I can't put the same number again, because then it won't be 1 to 1. It won't be a bijection, yeah? So I have to pick something different. Okay, so pick something different, but I have n minus 1 choices for that. Getting where I'm going with this? The third slot will have n minus 2 choices. And then n minus 3 choices, and so on. If you think about it, you're actually just going to factorial your way down all the way to 1. The answer is it's just n factorial. That's the size of Sn. It gets really big. When n increases in size, the group Sn gets really, really big in a hurry. Okay. I want to give you one more example of a group, which actually is sort of part of the symmetric group. So, but it's so important in and of itself that it's worth its own discussion. So let me put that one down here. And then I think we've got a pretty good list of some pretty important groups, although it's certainly not an exhaustive list and there'll be more to come. But at least we have a pretty good start here. So this will be one more example here, and this is going to be something called the dihedral group. And this one is denoted with a dn. And what this is, guys, is this is the set of all possible rotations. This is a little bit more of a geometric example. Rotations or reflections of an n-gon. Okay, so reflections and rotations of an n-gon, again, under composition. So, you know, these are actually permutations as well. And so you can talk about them like they are functions, and therefore they can be composed together. Let me kind of try to explain what I mean by this. I'm going to use a a small enough example that it isn't too overwhelming. Let's just take n equal to 4. Of course, a four-gon is just a square. Okay, by the way, I'm talking about a regular n-gon. I'm not talking about some awkward shaped thing right now. I just want to work with something where all of the sides are the same length. All of the angles are the same. So we're just going to take a look at a square. And I'm going to draw my square in a certain way. Let me get that in front of me here so I don't mess this up. Yeah, so I'm going to do 1, 2, 3, 4. I'm just going to number the corners of my square. So imagine that I start my square off looking like that. Okay, so what are the different rotations and reflections that I can do? So what I'm going to do is I'm going to draw pictures down here, guys, of the result of taking this square and doing rotations and reflections to it. Okay. Now, the first thing that I can do with this square, guys, is I can do nothing, right? I can leave it exactly the way it was presented to me. 1, 2, 3, 4, just like that. You won't be surprised to learn later that that's just my identity element. I've taken my square, I've picked it up, and I've set it right back down the same way it was. I've done nothing to it. It's like the identity permutation, right? Look at how the corners have moved. 1 went to 1, 2 went to 2, 3 went to 3, and 4 went to 4. That sounds like the identity permutation as if it was in the symmetric group. Yeah, it's kind of like that. But what I could do is I could, for example, I could do a 90-degree rotation, and I'm going to call this R, where I rotate the square. I'm going to rotate this thing by 90 degrees. So I'm going to do that. I pick up my square and I rotate it 90 degrees, and that's how it's going to look. A 90-degree rotation. Or I can do a 270-degree rotation, which will move the corners like that. Now this one, I'm going to write it as R squared because it's like I've rotated it twice by 90 degrees. So I'm just going to denote that with R squared. Okay, but of course I can keep going and rotate again. I can rotate 90 more degrees, and that's like doing 3 90-degree rotations. So that's just R cubed. Okay, so those are the rotations. Of course, if I rotate it again, right, you'll get back to the identity. So just in case anybody's wondering, R to the, in general, it will be N. If I do N rotations of my n-gon, I get back to where I started, which is just E. Okay. But I can also do some various rotation, some reflections as well. There's actually going to be 4 of these as well. So let me see if I can get these drawn correctly. So the first one is, let's imagine that I rotate across this horizontal line. So the 4 and the 1 goes to the bottom, and the 3 and the 2 comes up here like that, right? So it would look something like that, the 3, 2, and then the 4 and the 1. So it's like you've done some kind of a horizontal rotation. I'm going to use an H to represent that element. Or I could flip this original square along a vertical axis. And so the 1 and the 2 go to the left side, the 4 and the 3 go to the right side. So we'll call that one V. These are just letters that I'm making up. It doesn't really matter. Okay. And then we can also reflect across this diagonal line right here. Yeah. So if I did that, the 4 and the 2 stay in the same places, and I just switch the 1 and the 3. So that's a diagonal line. We'll call that D. And finally, I can also flip along the other diagonal line and leave the 1 and the 3 where they are and switch the 2 and the 4. I'm going to call that one T. Okay. Don't worry about memorizing these letters here down at the bottom. It's a little bit tricky. I will mention, though, that of course, what do you get if you reflect twice? If you do the same reflection twice, if you flip across some axis and then flip across that axis again, where do you end up at? Back where you started. which is the identity is the result of doing that, right? So all of these reflections, when you square them, when you do them twice, you get back to what you started with. Okay, whereas with the rotations, you have to go n times of these rotations to get back to where you started again. Yeah, so this is the dihedral group. I will point out, give myself a spot to write it down. Do you kind of see, by the way, that, well, first of all, Dn is a non-abelian group. If you do a rotation and then a reflection, you can check that the numbers do not end up in the same corners as if you first do that reflection and follow it by the rotation. So a rotation followed by a reflection can leave you with a different outcome than if you start with a reflection and then do a rotation. If you don't believe me, you should pause the video now and try to write out how that would look, right? How that would actually come about. Okay, so it's not going to be abelian, but it is going to be closed. If you do a composition of a rotation and a reflection, do two of those back to back, at the end of the day, what you have is some symmetry of this n-gon. You have done another rotation and reflection of this n-gon. It's associative because you're just doing composition of functions again, which is always associative. We've got our identity element right down here. It looks like all of the reflections are just their own inverses, right? So if you want to undo any reflection, the answer is to do that same reflection again. The 90-degree rotation would be the inverse of the 270-degree rotation, right? So in other words, if you did those back to back, that would be a total of 360 degrees. You'd be back to where you started. If I do a 180-degree rotation, that guy would be his own inverse, actually. So that's something to keep in mind. This is a group, but it's non-abelian. And I will point out the size of the group is actually 2n. So D4 has, as you can see, 8 elements in it. And this will always consist of n rotations. N of the elements look like rotations, and n of them look like reflections. I'm thinking of the identity element as if it was a rotation of 0 degrees. So it's part of that rotations set, if we want to think of it that way. So this is another example of a group. And I should point out that this group is actually sort of part of the symmetric group. I know that I haven't drawn the objects to look the same, but what we really are doing, guys, is a permutation of the numbers 1, 2, 3, and 4. You see that? You're starting with a particular configuration of the 1, 2, 3, and 4. 1, 2, 3, 4, right? And you're permuting those numbers into some other configuration. So for example, 1, 2, 3, 4 could turn into 3, 2, 1, 4, or 2, 3, 4, 1, or any number of these other 8 things. We're looking at permutations of the numbers 1 through 4. But we're not looking at all of them, right? Because after all, the size of S4, what was that again? It was 4 factorial, which is 24, which is much larger than D4, which has only 8 elements in it. These 8 right here. It's sort of like, well, what gives? What gives here, guys, is that these 8 permutations that we are seeing represented as rotations and reflections of a square are not giving us every possible permutation. Because look, when you look at this square, for example, can you ever have the 1 and the 3 right next to each other? You can't, can you? The 1 and the 3, if you look at any one of these 8 pictures, the 1 and the 3 are always on opposite corners of the square. They can't ever get shuffled to being adjacent. Well, but when you're doing permutations, when you're doing the larger symmetric group where anything goes as long as it's just a permutation, you'd be able to do more stuff with permuting those 4 numbers around in such a way that, yeah, you could actually not maintain the relative positions of the numbers on the corners of the square. Remember, with S4, you don't have a square. You're not looking at a square. You're just looking at permutations that can move numbers however they want, as long as it's a bijection. So that's why S4 has 24 elements, right? Whereas D4 only has 8 elements. In D4, we have to maintain the integrity of the square. The relative positions of the numbers have to remain the same. We're not tearing the square apart. We're not reorganizing it in a different manner. We're simply rotating or reflecting it. And so that's the difference. That's why DN is so much smaller than SN, even though we can think of these elements of DN as if they were permutations. It's kind of cool. In my next video, I'm going to talk about the concept of a subgroup. This is a group within a larger group. I've just given you a beautiful example of it. DN is a subgroup of SN, right? So this is another immense source of groups. To take a group that you already know, such as the symmetric group, and look inside of it at some smaller part of that big group that you started with, and you might find a smaller group inside of that bigger group. This is the concept of a subgroup, and I'm going to talk about that in my next video, which will therefore give us many more examples of groups. We've certainly seen a lot of them in this video. They are standard examples: the symmetric group, the integers mod n, matrices under either addition, or if we remove the non-invertible ones, under multiplication, and the dihedral groups, as you've seen right here, the quaternion group. These are all great examples of groups. I encourage you to study them, to get familiar with them, and to enjoy them as much as you can. They are going to be great examples for us as we continue to pursue the material. That's all I've got for this video, though, guys. Thank you so much for watching. I appreciate it, and I'll see you again next time. Bye for now.